Everything you see, every galaxy, every atom in your body might be a quantum accident. And that's the optimistic interpretation. Close your eyes. Not to imagine darkness, but to imagine less than darkness. Imagine the absence of absence. You can't, of course. Your mind rebels. It fills the void with something, anything. A black canvas, an empty stage, the pause between heartbeats. But that's cheating. Those are all something. Space is something. Time is something. Even the concept of waiting for something to happen requires a stage for the waiting to occur on. What we're reaching for is more radical than any human language was built to express. Not a room with the lights off, but a reality where the concept of rooms has been erased, where the grammar of existence itself has no past tense. Every creation story ever told begins with something already in place. The ancient Sumerians started with water. Genesis opens with void and darkness and the Spirit of God hovering. Three things, not zero. The Big Bang Theory, as taught in textbooks, begins with a singularity, an infinitely dense point, still something. Even when physicists talk about quantum fluctuations in the vacuum, they're describing a seething ocean of virtual particles, a background hum of fields and forces. Calling it nothing is polite fiction. It's nothing the way a silent room is empty, even though it's full of air and electromagnetic radiation and the ghosts of sounds your brain constructs from random noise. But what if we strip away even that? What if, at the very beginning, there was no singularity, no quantum foam, no laws of physics, no spatial dimensions, no time in which anything could happen? What if there was genuinely, absolutely, philosophically, nothing, and then, without cause or warning or mechanism, everything exploded into existence? This isn't mysticism. This isn't theology dressed in mathematical clothing. This is where cosmology has arrived after decades of observation, theory, and equations that refuse to stay on the chalkboard. The question isn't whether the universe had a beginning. We've measured the echo of that beginning, a faint microwave whisper that still bathes every cubic centimeter of space. The question is what, if anything, came before, and whether before is even a coherent word when time itself might be part of the created order. 13.8 billion years ago, there were 0 particles. Today, there are 10 to the 80th power. Something went catastrophically right, or catastrophically wrong, depending on your perspective. The universe either erupted from a state so improbable it should never have happened, or it emerged from a state so unstable that nothingness itself couldn't sustain its own non-existence. Both possibilities sound like the punchline to a cosmic joke. Here's what keeps physicists awake at night. Nothingness might be the most unnatural state conceivable. It might require more explanation than somethingness. Every calculation, every model, every attempt to describe a universe with truly 0 energy, 0 fields, 0 anything, suggests that such a state would be fantastically, breathtakingly unstable. It would last for exactly no time at all, which is fitting, because time wouldn't exist to measure its duration. The absence of everything might contain the seed of everything's arrival, not because of magic, but because of math, because quantum mechanics, which governs reality at its smallest scales, has something terrifying to say about empty space. It says that empty space isn't empty, can't be empty, and will do whatever it takes to fill itself. We're about to explore the most dangerous idea in science, that nothingness is unstable, that the universe doesn't require a creator, because nothing requires less explanation than something. That you and I and every star in the sky exist because, on the deepest level imaginable, nothing is a contradiction in terms. For most of human history, the origin of the universe wasn't a question. It was an answer. Different answers in different cultures, certainly, but always complete, always confident. The Egyptians knew the sun god Ra emerged from the primordial waters of Nun. The Norse watched Odin and his brothers carve reality from the corpse of the frost giant, Ymir. The Hindus understood that Brahma dreamed the cosmos into being through cycles of creation and destruction, each lasting billions of years. These weren't tentative hypotheses. They were certainties passed down through generations, encoded in ritual and scripture and the architecture of temples. Then came the scientific revolution, and certainty became uncomfortable. By the early 20th century, physicists had mapped the atom, bent light around the sun, and proven that matter and energy were interchangeable. But when it came to the universe as a whole, its origin, its age, its ultimate fate, they preferred to punt. The dominant view was the steady-state theory. The universe had always existed and always would. It might be expanding, yes, but new matter constantly bubbled up from nowhere to fill the gaps, maintaining a cosmic equilibrium that stretched infinitely in both directions through time. No awkward beginnings, no messy endings, just an eternal, self-sustaining machine. It was elegant. It was philosophically tidy. It was completely wrong. In 1929, Edwin Hubble aimed his telescope at distant galaxies and discovered something that should have been impossible. They were all moving away from us, not just drifting casually, but fleeing at speeds proportional to their distance. The farther away a galaxy was, the faster it receded. At first glance, this seemed to put Earth back at the center of everything, a geocentric throwback that Copernicus had demolished 4 centuries earlier. But the math revealed something far stranger. Space itself was expanding. Every point in the universe was moving away from every other point. Not because galaxies were traveling through space, but because the fabric of space was stretching like a balloon being inflated. Stand anywhere in the universe, and you'd see the same thing. Everything rushing away in all directions. Run that film backward. If the universe is expanding now, it was smaller yesterday. Smaller still last year. Smaller a billion years ago. Follow the trajectory far enough, and you arrive at a moment when all of space, all of matter, all of energy was compressed into a volume smaller than an atom. And before that, the equations break down. They divide by zero. They vomit out infinities. They scream that the rules of physics as we know them cease to apply. The universe, Hubble's data implied, had a beginning. This was not welcome news. Einstein himself had been so disturbed by the implications of his own equations, which naturally described a dynamic, evolving universe, that he'd added a fudge factor, the cosmological constant, to force the math to describe a static cosmos. When he learned of Hubble's discovery, he reportedly called it his biggest blunder. But his resistance wasn't just about being proven wrong. It was about what a beginning meant. If the universe had a starting point, what caused it to start? What lit the fuse? What existed in the moment before the first moment? And where did it come from? Causality itself was under threat. Every event in our experience has a cause. You exist because your parents met. They exist because their parents met. The Earth exists because a cloud of dust collapsed under gravity 4.5 billion years ago. That dust exists because earlier generations of stars forged heavy elements and exploded. Those stars exist because quantum fluctuations in the early universe grew into density variations. But if you trace this chain of causes all the way back to the beginning, you hit a wall. What caused the Big Bang? And if something caused it, what caused the cause? Either you accept an infinite regress, causes stacked on causes forever, which explains nothing, or you accept a first cause that itself had no cause, which violates everything we know about how reality works. Many scientists hated this. Fred Hoyle, the British astronomer who championed the steady-state model, coined the term Big Bang as an insult, a mocking label for what he saw as quasi-religious nonsense smuggled into physics. He wasn't wrong to be suspicious. The idea that the universe popped into existence from nothing, for no reason, at a specific moment in time, sounds less like science and more like Genesis with equations. The fact that Georges Lemaitre, the physicist who first proposed the expanding universe model, was a Catholic priest didn't help perceptions. Critics accused him of trying to prove God through calculus, but the evidence kept piling up. In 1964, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate an annoying hiss from their radio antenna. They couldn't get rid of it. It came from every direction in the sky, uniform and constant. They checked for interference. They cleaned pigeon droppings out of the equipment. The hiss remained. What they'd stumbled onto was the cosmic microwave background, the afterglow of the Big Bang itself, a faint radiation that has been cooling and stretching for nearly 14 billion years. It's still there, bathing every cubic centimeter of space in a glow that's now just 3 degrees above absolute zero. It's the oldest light in the universe, the echo of creation, and it matches the predictions of Big Bang cosmology with unnerving precision. The universe had a beginning. That much became undeniable. But what kind of beginning? The Big Bang wasn't an explosion in space, the way a firework detonates in the night sky. It was an explosion of space itself. There was no pre-existing void for it to expand into, no arena that contained it. Space and time came into being together, erupting from a state of unimaginable density and temperature. In the first fraction of a second, the universe was smaller than a proton and hotter than 1 trillion suns. Matter and energy were interchangeable. The laws of physics were still congealing, like ice forming on a pond. Imagine rewinding a film reel until the reel itself disintegrates. That's the Big Bang barrier. You can't look beyond it using the tools of conventional physics because those tools depend on space and time existing. You can't ask what happened before because before is a temporal concept, and time hadn't been invented yet. Hawking called it asking what's north of the North Pole. The question seems to make sense, but it's grammatically incoherent. The coordinates break down, yet the question gnaws at us. If the Big Bang created time, what does before even mean? Can a question exist if the grammar of the question is impossible? And if the question is meaningless, why does it feel so urgent, so necessary to answer? Every moment you've lived depends on the universe choosing to exist. Why did it bother? Here's where the vertigo really sets in. The laws of physics that govern our universe, the strength of gravity, the charge of the electron, the mass of the quarks, are exquisitely fine-tuned. Change any of them by even a tiny fraction, and the universe becomes inhospitable to life. Make gravity slightly stronger, and stars burn out too fast for planets to form. Make it weaker, and matter never clumps into galaxies. Tweak the strong nuclear force, and atomic nuclei fall apart or refuse to form. Adjust the electromagnetic force, and chemistry as we know it becomes impossible. The odds of all these constants landing in the narrow range that allows for complexity, for stars, for planets, for life, are stupefyingly small. 1 in 10 to the 229th power. That's not a number. It's an obscenity against probability. It's like flipping a coin and having it land on its edge, then doing that again 1,000 times in a row. The universe didn't just roll a natural 20 on its character stats. It rolled 20s on dice that have trillions of sides. 3 possibilities emerge, and cosmologists have spent decades arguing over which one to bet on. The first is coincidence. The constants are what they are, no explanation needed. Deal with it. This is deeply unsatisfying and feels like giving up. The second is design. Some intelligence, some mechanism, some principle we don't yet understand tuned the universe for life. This opens the door to theology, which makes scientists twitchy, though a few have walked through it anyway. The third possibility is that our universe isn't alone, that the Big Bang created not one cosmos, but countless variations, each with different physical laws, and we naturally find ourselves in one of the rare universes where observers can exist. This is the multiverse hypothesis, and it means reality is far stranger than any religion ever imagined. But all 3 possibilities dodge the deeper question. They explain why our universe has the properties it does, but not why there's a universe at all. You can invoke a multiverse, but then you have to explain where the multiverse came from. You can invoke a designer, but then you have to explain where the designer came from. You can invoke blind chance, but then you have to explain why the rules of probability themselves exist. Every answer generates a new question. Every explanation requires a deeper explanation. The regress continues. Unless there's a way to break the chain, a way for existence to bootstrap itself into being without requiring anything prior. A way for something to come from nothing, not through magic, but through necessity. This is where quantum mechanics enters the picture, and where everything gets weird. In the classical physics of Newton and Einstein, empty space is truly empty. A vacuum is a vacuum, no matter, no energy, no fields, just geometric nothingness. But quantum mechanics says otherwise. At the smallest scales, the fabric of reality seethes with activity. Particles and antiparticles constantly blink into existence in pairs, annihilating each other almost instantly. These are called virtual particles, and they're not theoretical curiosities. They have measurable effects. They alter the behavior of atoms. They create forces between metal plates in a vacuum. The quantum vacuum isn't empty. It's a roiling sea of potential, a background hum of energy that can never be silenced. And here's the kicker. Quantum mechanics allows for something called vacuum fluctuations. Tiny, random variations in energy that pop up and vanish on timescales too brief to violate the laws of thermodynamics. Usually these fluctuations are microscopic, fleeting, irrelevant to anything larger than an atom. But the math doesn't put an upper limit on their size. In principle, a sufficiently large fluctuation could create a bubble of space-time, a pocket universe that inflates and persists, not because anything caused it, but because quantum uncertainty permits it. Because, at the deepest level, nothing is unstable. Run that simulation long enough, and eventually you'll get a fluctuation big enough to become a universe. not a likely fluctuation. But in an infinite expanse of time, or whatever passes for time in the pre-universe void, even the absurdly unlikely becomes inevitable. Given enough chances, even a coin can land on its edge. This is the razor's edge cosmology now walks. The Big Bang marked the beginning of our universe, the moment when space and time as we know them came online. But it might not be the beginning of everything. There might be a larger reality, a quantum substrate, a deeper layer of existence where the rules are different and where universes can bubble into being like foam on an ocean. If that's true, then the Big Bang wasn't creation ex nihilo. It was a phase transition, a cosmic birth canal, an emergence from something stranger than nothing. But if space itself was created, if time itself began, then what was the stage before the stage? What is the arena in which universes appear? And if that arena itself had to come from somewhere, are we just kicking the problem upstairs, explaining mystery with deeper mystery? The equations don't tell us. They hit a wall called the Planck epoch, the first 10 to the minus 43 seconds after the Big Bang, where quantum effects and gravitational effects become equally important, and our theories stop working. Before that threshold, we're blind. We have no theory of quantum gravity, no unified framework to describe what happens when space-time itself is as small and jittery as a subatomic particle. String theory offers hints. Loop quantum gravity offers different hints. Both remain unproven, mathematical castles built on elegant but untested foundations. We stand at the edge of knowledge, staring into the abyss before the beginning, knowing that the answers we seek might require rewriting the deepest rules of reality. And the most unsettling part? The answer might not bring comfort. It might reveal that existence is even more contingent, more fragile, more accidental than we feared. Or it might reveal that nothing was never an option at all. Lawrence Krauss says the universe came from nothing. Philosophers say he's cheating. Both might be right. The word nothing seems simple. It's what's left when you remove everything. Take away the furniture from a room, you have an empty room. Take away the air, you have a vacuum. Take away the room itself, you have... What exactly? Your intuition insists there should be an answer. Some final state of absolute absence, where literally nothing remains. No matter, no energy, no space, no time, no laws, no potential. Just pure, unqualified nothingness. The canvas before the painter arrived. The silence before the first sound. The void before God said, "Let there be light," minus the God and the saying and the potential for light. But here's the problem. The more precisely physicists tried to define nothing, the more it slipped through their fingers. What seemed like a straightforward concept, the absence of things, turned out to be layered, ambiguous, and possibly incoherent. Because quantum mechanics, that bizarre rule book governing reality at its smallest scales, has something devastating to say about emptiness. It says that emptiness doesn't exist, that the vacuum of space, the most nothing-like thing we can actually study, is seething with activity at every instant. That even if you removed every particle, every atom, every photon from a region of space, you wouldn't have nothing. You'd have something profoundly strange. Take a cubic centimeter of empty space. Not the space between stars, which is actually filled with thin gas and dust and stray hydrogen atoms. We're talking about the hardest vacuum achievable, a region where every last particle has been cleared out. Classical physics says this space should be perfectly inert, a stage waiting for actors, but currently vacant. Quantum mechanics laughs at this picture. In that cubic centimeter, quantum fields generate and annihilate 10 to the 29th power virtual particles per second. That's a 1 followed by 29 zeros. Every second, in every cubic centimeter. Nothingness is the universe's busiest factory. Virtual particles aren't metaphors. They're not mathematical conveniences that we use in calculations, but don't really exist. They have measurable, tangible effects. Place two metal plates extremely close together in a vacuum, and they'll experience a tiny attractive force pushing them together. This is called the Casimir effect, and it happens because the virtual particles between the plates are constrained. Only certain wavelengths can fit in the gap, while the virtual particles outside have no such restriction. The imbalance creates a pressure difference. The vacuum pushes. You can measure it with sensitive instruments. The nothing between those plates behaves like something, because at the quantum level, there is no such thing as empty space. This happens because of the Heisenberg uncertainty principle. Sapientielheit, one of the foundational rules of quantum mechanics. It says that certain pairs of properties, like energy and time, can't both be precisely known. The more accurately you know one, the less accurately you can know the other. And here's where it gets weird. Over very short timescales, the uncertainty in energy becomes large. Large enough that the universe can temporarily borrow energy from nowhere. To create particle-antiparticle pairs that pop into existence, exist for a fleeting instant, then annihilate back into the vacuum. These fluctuations don't violate energy conservation because they happen so fast that the violation can't be measured. It's like the universe is taking out loans and repaying them before the cosmic auditor notices. So, when physicists talk about the quantum vacuum, they're not describing nothing in any intuitive sense. They're describing a roiling sea of fields, electromagnetic fields, electron fields, quark fields, all vibrating at their ground state, their lowest possible energy level. But lowest possible isn't zero. It's a baseline hum that can never be silenced. These fields are fundamental. They're woven into the fabric of space itself. They're not objects sitting in space. They're part of what space is. And as long as space exists, these fields exist. And as long as these fields exist, they're doing this quantum flickering dance. This brings us to the first level in the hierarchy of nothingness. Level 1. Empty space with quantum fields. This is what physicists often mean when they casually say vacuum or nothing. It's the absence of real, persistent particles, but not the absence of the underlying quantum substrate. It's a nothing that's actually something, and that something is profoundly active. When Lawrence Krauss wrote A Universe from Nothing, this is the nothing he was primarily discussing. He argued that quantum fluctuations in this kind of vacuum could, given the right conditions, inflate into an entire universe. That the Big Bang might have been the ultimate vacuum fluctuation, a bubble that grew too large to collapse back. It's a bold idea. It's backed by serious physics, and it drove philosophers absolutely insane. David Albert, a philosopher of physics at Columbia University, wrote a scathing review of Krauss's book. His core objection was simple and devastating. If your nothing includes quantum fields, laws of physics, and a framework for things to emerge from, then you're not talking about nothing. You're talking about something, and you've just relabeled it to make your argument work. Calling a quantum vacuum nothing is like calling a pregnant woman not a mother yet. Technically true in one sense, misleading in the deeper sense. The quantum vacuum has properties, structure, dynamics. It's governed by equations. It exists in time, even if time is weird and quantum at that scale. This isn't philosophical nitpicking. It's a fundamental challenge to the claim that science has explained how to get something from nothing. Because if the nothing you start with is already something, you haven't solved the problem. You've just pushed it back one step. Krauss's response was that philosophers are asking for a kind of nothing that's physically meaningless. That absolute philosophical nothing. No space, no time, no fields, no laws, is a concept that has no connection to reality and therefore no place in a scientific discussion. He's not entirely wrong. Science deals with testable hypotheses, observable phenomena, mathematical models. Absolute nothing, by definition, has no properties to study, no behavior to predict. It's a black hole in the epistemological sense. You can't build a theory around it because there's nothing for the theory to describe. But the philosophers aren't wrong either. Because the question, why is there something rather than nothing, is fundamentally a question about the absolute version. When theologians invoked creatio ex nihilo, creation from nothing, they meant nothing, nothing. Not quantum vacuum nothing, not Platonic realm of forms nothing, not pre-existing laws of physics nothing. They meant the absence of being itself. And if you're going to claim that science has answered that question, you'd better be sure you're answering the same question, not a watered-down version. This tension brings us to the second level of nothingness, which is stranger and harder to conceptualize. Level 2. No space, no matter, no energy, but the laws of physics still exist. This is the kind of nothing that might have preceded the Big Bang if the Big Bang came from a prior state rather than absolute absence. In this scenario, the stage is gone, the actors are gone, but the script remains. The equations that govern reality persist, even when there's no reality for them to govern. It's like having the rules of chess without a board or pieces or players floating in some abstract conceptual realm, waiting for a game to begin. This might sound absurd, but it's actually a coherent position. The laws of physics, in this view, aren't things that the universe contains. They're descriptions of how the universe must behave if it exists. They're logical necessities, mathematical truths that would be true even if nothing instantiated them. The Pythagorean theorem doesn't depend on triangles existing. It's a relationship between abstract numbers. If triangles exist, they obey the theorem. If they don't, the theorem is still true in the Platonic sense. Maybe the laws of physics are like that. Maybe they're eternal, necessary structures. And the universe is just one possible realization of those structures. But this just shifts the mystery. Why these laws and not others? Why laws at all? If the laws of physics are eternal and necessary, what makes them necessary? Is there a meta-law that determines which laws can exist? And if so, where does that come from? You've replaced the question, why is there a universe, with the question, why are there laws? Which doesn't feel like progress. It feels like repainting the problem. And then there's level 3. Absolute nothing. No space, no time, no quantum fields, no laws of physics, no mathematical structures, no logical frameworks, no potential for anything to exist. Pure, unqualified, metaphysical nothingness. Nothing isn't a blank canvas. It's the moment before someone invents the concept of canvases. It's the absence of absence, the void that can't even be called a void because calling it something gives it an identity. Can this exist? Not, can it have existed before the universe? But can it exist even as a coherent concept? Some philosophers argue that absolute nothing is logically impossible, that the moment you start talking about it, You've given it properties. The property of being absolute, the property of being nothing, the property of being discussable. That trying to conceive of it is like trying to draw a square circle. The words fit together grammatically, but they don't correspond to anything real or possible. Others argue that absolute nothing is not only possible but the default state, and that something existing is what requires explanation. That the natural state of affairs is non-existence, and existence is a bizarre aberration that needs justification. In this view, the universe is the thing that's weird and unnatural, not the absence of a universe. Being is the anomaly. Nothing is what we should expect. If nothingness is impossible, then something is eternal. That's either comforting or nightmarish, depending on what that something is. If it's a quantum substrate, a field of potentiality, then existence has always been on the edge of happening, waiting for the right fluctuation. If it's a multiverse generator, then reality is far larger and stranger than we imagined, and our universe is one bubble in an endless foam. If it's a conscious designer, then we're back to theology. If it's just the abstract necessity of mathematical laws, then we live in a kind of Platonic cage, where everything that can happen must happen, somewhere, somewhen. But there's another wrinkle, another way to slice the problem that makes the question of nothing even more slippery. It's called the zero-energy universe hypothesis, and it's one of the most elegant ideas in cosmology. The argument goes like this. Matter and energy are positive. They add to the universe's energy budget. But gravity is negative. Gravitational potential energy represents a deficit, a hole in the energy ledger. When you lift a rock, you're increasing its gravitational potential energy, which means you're making it less negative, which means you're adding energy to the system. Conversely, when objects fall together, they release energy, and their potential energy becomes more negative. Add it all up, all the matter, all the radiation, all the energy in the universe, and all the gravitational potential energy binding it together, and the total might be zero. Exactly zero. Not approximately, not within measurement error, but precisely, perfectly zero. If that's true, then the universe's energy budget is balanced. The universe hasn't borrowed anything. It hasn't violated conservation of energy. It emerged from a state with zero energy and remains at zero energy, just distributed differently. The positive and negative sides of the cosmic ledger cancel out completely. This means the universe could emerge without violating conservation laws. It wouldn't need an external source to provide energy because it's not consuming any net energy. It's a closed loop, a self-balancing equation. In this view, the universe isn't something that was created at the expense of nothing. It's a rearrangement of nothing. It's what you get when you take zero and split it into +1 and -1. The total is still zero. Nothing has been added to reality's balance sheet. Existence becomes a cosmic accounting trick. This is deeply appealing to physicists because it removes one of the major objections to the universe coming from nothing. If the universe had a net positive energy, you'd have to explain where that energy came from, and you'd be stuck invoking an external source, which feels like giving up. But if the universe is a zero-energy system, it can bootstrap itself into existence. It doesn't need a cause because it's not consuming any resources. It's the ultimate free lunch, except it's not even a lunch. It's rearranging your plate to look like there's food on it when the total mass of food remains zero. But does this actually solve the problem? You still need the rules that allow this rearrangement to happen. You need quantum mechanics to permit fluctuations. You need space-time to exist so that matter and gravity can cancel each other out. You need the laws of thermodynamics, the principles of symmetry, the mathematical framework that makes zero a meaningful concept in the first place. All of that is still something. The zero-energy hypothesis explains why the universe doesn't violate energy conservation, which is important. But it doesn't explain why there's a framework in which energy conservation is a rule. Krauss argues that this is as close to from nothing as you can get while still doing science. That asking for anything beyond this is asking for magic, not physics. That the quantum vacuum, with its fields and fluctuations and zero-energy budget, is the scientific definition of nothing. And if philosophers want a different definition, they're welcome to it. But they're not doing physics anymore. The philosophers fire back that this is equivocation, that if you define nothing as the kind of nothing that can produce something, then of course you've explained how something comes from your definition of nothing. You've rigged the game. It's like defining bachelor as unmarried man, or married man named Steve, and then triumphantly announcing that Steve is a bachelor despite being married. You've changed the meaning of the word to make your conclusion true, and both sides are talking past each other because they're not actually disagreeing about the physics. They're disagreeing about what question is being asked. Krauss is answering, can a universe emerge from a quantum vacuum without violating physical laws? The answer is yes, probably, under certain conditions. The philosophers are asking, why is there a quantum vacuum and physical laws instead of absolutely nothing? And that question remains unanswered. Maybe it's unanswerable. Maybe it's incoherent. Maybe it's the deepest question there is. So, did the universe come from quantum nothing? Or is that just redefining the word to win the argument? And if it's not really nothing, what do we call the state it came from? And if that state had properties, laws, potential, then where did those come from? Are we chasing an infinite regress? Or is there a stopping point, a foundation that doesn't itself require explanation? The uncomfortable truth is that we don't know. We have models, equations, theories that push the boundary of ignorance back further and further. But every answer opens new questions. Every solution reveals deeper mysteries. And the ultimate mystery, why there's something rather than nothing, might be the one question that forever eludes a final answer. Not because we're not smart enough, but because the question itself might be standing outside the boundaries of what questions can meaningfully ask. Quantum mechanics says particles can appear from nothing. So why not an entire universe? The math actually works. To understand how reality might bootstrap itself into existence, we need to descend into the quantum realm, where the rules that govern everyday life dissolve into something far stranger. This isn't a journey into empty space. It's a journey into the fabric that makes space possible, the substrate beneath the substrate, the foundation that has no foundation. Welcome to quantum field theory, where everything you think you know about existence needs to be rebuilt from scratch. Start with a field, not a field of wheat or a magnetic field in the classical sense, but something more fundamental. Imagine a wave that doesn't need an ocean. That's a quantum field, the universe's baseline hum. Every type of particle in existence corresponds to a field that permeates all of space. There's an electron field, a quark field, a photon field. These fields aren't made of anything more basic. They're the bottom layer. When you see an electron, you're seeing an excitation in the electron field, a ripple that has enough energy to persist and behave like a discrete particle. But the field itself is always there, even when no particles are present, vibrating at its minimum energy state. And here's where it gets uncomfortable. That minimum energy state isn't zero. Can't be zero. The Heisenberg uncertainty principle forbids it. This principle, one of the foundational rules of quantum mechanics, says that certain pairs of properties can never be simultaneously known with perfect precision. The more accurately you measure one, the less accurately you can know the other. Position and momentum are linked this way. So are energy and time. What this means is visceral and strange. Over very short timescales, durations comparable to the time it takes light to cross an atomic nucleus, the uncertainty in energy becomes enormous, large enough that the universe can temporarily violate energy conservation, as long as the violation is brief. Energy can be borrowed from the vacuum, conjured from apparent nothingness, used to create particle-antiparticle pairs, and then paid back before the cosmic bookkeeper notices. It's not that energy conservation is broken. It's that on sufficiently small timescales, the concept of how much energy is here becomes fuzzy, indeterminate, smeared out over a range of possibilities. This isn't theoretical speculation. It's embedded in every calculation quantum physicists make. Virtual particles, those fleeting particle-antiparticle pairs that pop in and out of existence, contribute to the behavior of real particles in ways we can measure. They shift the energy levels of electrons in atoms, creating tiny corrections called the Lamb shift. They alter the magnetic moment of the electron with precision that matches experimental measurements to 10 decimal places. They create a force between metal plates in a vacuum, the Casimir effect, that can be detected with equipment you could build in a decent university lab. The quantum vacuum, this supposed nothingness, has fingerprints all over observable reality. In other words, empty space isn't passive. It's an active participant in physics, constantly creating and destroying, fluctuating and seething, never truly at rest. Now shrink your perspective. Zoom in past atoms, past protons, past quarks, down to the smallest meaningful scale in physics. This is the Planck length, approximately 10 to the negative 35th meters. To put that in context, a Planck length is to an atom what an atom is to the entire observable universe. It's the scale where quantum mechanics and general relativity both become important, where gravity and quantum uncertainty collide. And at this scale, space-time itself stops being smooth. It becomes chaotic, turbulent, foamy. This is the quantum foam. Space-time at the Planck scale doesn't look like the neat geometric grid you see in textbooks. It looks like the surface of boiling water, except the bubbles aren't bubbles. They're micro wormholes, tiny pockets where the geometry of space writhes and contorts. Dimensions might split apart and reconnect. Causality becomes negotiable. The distinction between past and future blurs into quantum superposition. These aren't permanent features. They flash in and out of existence on timescales of 10 to the negative 43rd seconds. The Planck time, the smallest duration that has physical meaning. Below that scale, the very concept of before and after dissolves. You might be wondering, if space-time is this chaotic at small scales, why does the universe seem so smooth and orderly at larger scales? Same reason an ocean looks like a flat surface from an airplane, even though it's made of churning water molecules. Average over enough quantum fluctuations, and they cancel out, leaving a stable, predictable geometry. But zoom in close enough, and the stability is an illusion. The fabric of reality is seething, and here's the leap. If the vacuum can borrow energy to create particle pairs, and if space-time itself is a quantum field bubbling with activity, then why can't a universe be a quantum fluctuation? Why can't an entire cosmos, with all its matter and energy and space-time, tunnel into existence from a prior state of nothing, or near nothing, the same way an electron-positron pair tunnels out of the vacuum? This is where quantum cosmology enters, and where the math becomes almost surreally abstract. Alexander Vilenkin, a cosmologist at Tufts University, proposed exactly this scenario in the early 1980s. His idea: the universe began as a quantum tunneling event from a state of nothing. Not the quantum vacuum nothing we've been discussing, but a state even more minimal. No space, no time, just a mathematical potential. In quantum mechanics, particles can tunnel through energy barriers that classical physics says they shouldn't be able to cross. An electron can appear on the other side of a wall without passing through it, not because it teleports, but because its wave function extends into the classically forbidden region, giving it a small probability of being detected there. It's bizarre, it defies intuition, and it happens constantly in the quantum world. Vilenkin applied this logic to the universe itself. In his model, you start with nothing, or more precisely, with a state of zero spatial volume and undefined time. The wave function of the universe, the mathematical object that describes all possible configurations the cosmos could have, extends into the region where universes exist. And just like an electron tunneling through a barrier, the universe can tunnel from no universe to universe with a small but non-zero size. Once it exists, it can inflate, expand, evolve into the cosmos we observe. No external cause needed. No violation of energy conservation, because the total energy remains zero. Just a quantum probability that, given infinite opportunities, eventually actualizes. In other words, the universe might not have been created. It might have been probabilistically inevitable. Stephen Hawking and James Hartley took this idea even further with their no-boundary proposal. Imagine trying to trace the history of the universe backward in time, running the film in reverse, watching galaxies merge, stars collapse, the cosmic microwave background grow hotter and denser. As you approach the Big Bang, space-time becomes more and more curved, more and more compact, until you reach a point where the usual rules break down. In classical general relativity, you'd hit a singularity, a point of infinite density where the equations vomit out nonsense. But Hawking and Hartley argued that quantum mechanics smooths out the singularity. Time, in their model, doesn't have a sharp beginning. Instead, as you approach the Big Bang, time gradually becomes more and more space-like. The distinction between temporal and spatial dimensions blurs and eventually dissolves. Picture it this way. Take a globe. The North Pole is a point, a single location. Ask what's north of the North Pole, and the question is meaningless. There is no north of the North Pole. That's the boundary, but it's not an edge. You don't fall off. You just stop being able to go further in that direction. In the Hartle-Hawking model, the Big Bang is like the North Pole. It's a boundary to time, but not a sharp edge where something suddenly begins. Instead, time smoothly curves into something that looks more like space. And the question, what came before, becomes as meaningless as what's north of the North Pole. The universe is finite in time, but has no beginning, no initial moment, no singularity. It's boundaryless, self-contained, requiring nothing outside itself to explain its existence. This model uses a tool called the path integral formulation, originally developed by Richard Feynman for quantum mechanics. The idea is that a quantum system doesn't take one path from state A to state B. It takes every possible path simultaneously. Each path contributes to the final probability amplitude, and when you add them all up, some paths interfere constructively, some destructively, and what emerges is the probability of the system ending up in a particular configuration. Feynman applied this to particles moving through space. Hawking and Hartley applied it to the entire universe moving through time, or rather, through a mix of time and imaginary time, a mathematical trick where time is treated as a complex number, allowing calculations that would otherwise be impossible. The result is the wave function of the universe, a single mathematical object that encodes every possible history the cosmos could have, weighted by probability. In this framework, asking what caused the Big Bang is like asking what caused the North Pole to be at the top of the Earth. The question presumes a framework, a boundary in time that needs crossing, a before that needs explaining, that the model explicitly denies exists. The universe doesn't have a cause, because causation requires time, and time is part of the thing being explained. In other words, the universe might not have come from anything. It might simply be in the same way a mathematical theorem is, with no external reference point required. But let's pause here and feel the full weight of what's being proposed. We're saying that reality itself, space, time, matter, energy, everything, is a quantum phenomenon. That the cosmos is less like a machine that was built and more like a wave function that collapsed, or never collapsed. That it exists in a superposition of all possible histories, and we're living in one branch of that superposition, selected not by design or intent, but by the brute fact that it's a branch where observers can exist to ask the question. This is the ultimate application of the anthropic principle. We find ourselves in a universe that permits our existence because we couldn't find ourselves anywhere else. The universe doesn't need to be likely. It just needs to be possible. And if you're feeling dizzy, good. This is the edge of human comprehension. We're using mathematical tools designed to describe electrons and photons and applying them to existence itself. We're treating the universe not as an object in space, but as a quantum state in an abstract configuration space. We're asking whether reality is deterministic or probabilistic at the most fundamental level, and the answer seems to be probabilistic, which means every moment of your life rests on an infinite tower of quantum dice rolls, any one of which could have gone differently if you weighed 10 to the 10 to the 56th power years, a number so large that writing it out would require more atoms than exist in the observable universe. A Boltzmann brain will spontaneously form in the quantum foam. A conscious mind, fully formed, complete with false memories and a sense of continuity, assembled by random fluctuations. It will exist for a fraction of a second before dispersing back into chaos. Statistically, if the universe lasts forever and vacuum fluctuations continue indefinitely, Boltzmann brains will eventually outnumber naturally evolved brains by a ratio so large it might as well be infinity. Which raises the disturbing question, are you one? Probably not. The math suggests that evolved observers in structured universes should dominate in the early epochs. But probably not isn't a proof. It's a bet. Every moment, trillions of potential universes flicker at the edge of existence. Ours is the one that stuck. Or did it? Maybe all of them stuck. Maybe quantum mechanics doesn't choose between possibilities. Maybe it realizes all of them in parallel branches we can't access. Maybe there's a version of reality where the quantum fluctuation that could have become our universe didn't inflate, didn't persist, collapsed back into the foam after a microsecond. Maybe there's a branch where Earth never formed, where the molecular cloud that became our solar system dispersed instead, where you were never born. And maybe all of these branches are equally real, equally valid, coexisting in a vast multiverse where every quantum possibility is actualized somewhere. This is the many worlds interpretation of quantum mechanics, and it's less fringe than it used to be. It solves the measurement problem: why quantum systems seem to collapse into definite states when observed, by saying they don't collapse. The wave function never collapses. Every possible outcome happens. When you measure a quantum system, you become entangled with it, and the universe branches into versions where each outcome occurred. You only experience one branch, so it feels like collapse, but the other branches are just as real. They're just inaccessible. You can't visit the branch where the cosmic ray that just passed through your brain struck a different neuron and altered your thought process. But that branch exists, and a version of you is living it, having a slightly different thought. Apply this to cosmology, and you get eternal inflation. Our Big Bang wasn't the only one. It was one bubble in an infinite foam of inflating regions, each with different physical laws, different constants, different outcomes. Some bubbles produce universes capable of supporting life. Most don't. We necessarily find ourselves in one of the rare ones, not because it's special, but because it's the only type where observers can arise to ask the question. The multiverse isn't a hypothesis designed to explain fine-tuning. It's a prediction that falls out of inflation plus quantum mechanics. If inflation happened, and the evidence strongly suggests it did, then it's almost impossible to shut off. Once it starts in one region, it creates more inflating regions, which create more, in an exponential cascade that never ends. The universe isn't just big. It's infinitely big, infinitely varied, and our observable patch is an infinitesimal speck in an endless ocean of possibility. In other words, the universe might not be unique. It might be one outcome among countless others, all equally real, all equally valid. But here's the problem, the hook that we've been avoiding. All of this, quantum mechanics, vacuum fluctuations, the uncertainty principle, the wave function of the universe, the path integral formulation, the Hartley-Hawking proposal, all of it rests on rules. The rules of quantum mechanics, the structure of quantum field theory, the principles of symmetry and conservation, the mathematics that describes how fields interact, how particles tunnel, how probabilities add up. These rules are incredibly specific. They're not arbitrary. Change them even slightly, and the whole edifice collapses. You don't get universes tunneling from nothing. You don't get vacuum fluctuations. You might not even get math that's logically consistent. So where did the rules come from? If the universe is a quantum fluctuation, fine. But quantum mechanics needs rules to work. The Schrödinger equation doesn't explain itself. The uncertainty principle doesn't justify its own existence. The path integral formulation presumes a mathematical framework where integrals make sense, where complex numbers exist, where the concept of a sum over all possible paths is meaningful. And that framework exists. Where? In what space? Governed by what meta-rules? You can say the rules are eternal, that they've always existed in some abstract Platonic sense. But then you're just replacing the mystery of why is there something rather than nothing with the mystery of Why are there these rules rather than no rules, or different rules? You can say the rules are necessary, that they couldn't have been otherwise, that mathematical logic constrains what's possible. But then you need to explain why mathematical logic itself exists, why the universe is compelled to obey it, why necessity is binding. Or you can say the rules emerged from something deeper, some more fundamental layer of reality that we haven't discovered yet. But then you're kicking the problem upstairs again, because that deeper layer has its own rules, its own structure, its own logic. And where did that come from? Do we just get an infinite tower of turtles? Rules explaining rules explaining rules, with no foundation? The quantum foam churns. The vacuum fluctuates. Universes tunnel from nothing, or from something that looks like nothing if you squint. And all of it, every bit of it, dances to a choreography that was written before the first dancer took the stage. The question isn't just whether the universe came from nothing. It's whether nothing could ever have existed in the first place, given that the alternative requires rules, and rules are themselves something. We've descended to the Planck scale and found that space-time is a quantum field, seething with possibility. We've traced the math that shows a universe can tunnel into existence without violating conservation laws. We've explored models where time curves back on itself, where beginnings dissolve into boundaryless geometry, where the Big Bang is the North Pole of temporal space. And at the bottom of it all, beneath the equations and the fluctuations and the wave functions, we find not an answer, but a deeper question. Not a foundation, but an abyss that stares back. The math works. The universe could come from quantum nothing. But quantum nothing isn't nothing, and the rules that allow it to not be nothing are themselves something. And we're back where we started, staring at existence, wondering why there's this instead of that, this instead of nothing, anything instead of the void. The quantum foam gives us a mechanism. It doesn't give us a reason. And maybe reason is the wrong thing to look for. Maybe causation, explanation, justification, all those concepts we use to make sense of the world are tools that break when you apply them to the world itself. Or maybe we're just not asking the right question. Yet, if the laws of physics are eternal, they're more real than reality. If they're not, then the universe wrote its own instruction manual. Neither makes sense. We've traveled deep into the quantum realm and emerged with a mechanism. Vacuum fluctuations, tunneling from nothing, the wave function of the universe, mathematical frameworks that show how a cosmos can bootstrap itself into existence without violating energy conservation, without requiring an external creator, without needing anything to exist beforehand, except the rules that govern quantum behavior. It's elegant. It's backed by decades of experimental confirmation. It pushes the boundary of explanation further than any previous generation dared to dream. But it doesn't solve the problem. It deepens it, because quantum mechanics is itself a law, a very specific set of rules about how reality behaves when you look at it closely enough. The Schrödinger equation, which describes how quantum states evolve over time, is an exquisitely precise piece of mathematics. The uncertainty principle isn't a vague suggestion. It's a hard constraint with a specific numerical value. The structure of quantum field theory, with its symmetries and conservation laws and particle interactions, is intricate and non-negotiable. Change any of these rules, even slightly, and you don't get a different version of quantum mechanics. You get incoherence. The math breaks. Predictions contradict observations. Reality as we understand it becomes impossible. So where did these rules come from? If the universe emerged from quantum fluctuations, fine. But what gave rise to the fluctuations? What established the framework in which fluctuation is possible? You can't invoke quantum mechanics to explain the origin of the universe and then refuse to explain the origin of quantum mechanics itself. That's just moving the mystery one step back and declaring victory. It's turtles all the way down, except you've stopped looking after the first turtle and convinced yourself you've reached bedrock. Laws of physics aren't written on tablets. They're more like the grammar rules of a language that writes itself. Except grammar rules don't write themselves. Languages emerge from communities, from usage, from evolutionary pressures acting on communication. But the laws of physics have no community, no context, no evolutionary history that we can point to. They just are. Or are they? Did they always exist, eternal and unchanging, waiting in some platonic realm for a universe to instantiate them? Or did they emerge alongside the universe, perhaps even because of it? Rules that crystallized out of a deeper, more primordial chaos. This is where physics splits into camps, and the arguments get philosophical in ways that make some scientists uncomfortable. There's no experiment you can run to definitively settle these questions. No measurement that will tell you whether mathematics exists independently of physical reality. No telescope that can see beyond the boundaries of causation to check what, if anything, preceded the rules. You're left with competing metaphysical frameworks, each internally consistent, each explaining the same observations, and no empirical method to choose between them. The first camp is Platonism in physics, the idea that mathematical structures exist independently of the physical universe, eternal and immutable, in some abstract realm beyond space and time. In this view, the laws of physics aren't descriptions we invented to make sense of observations. They're discoveries. We're uncovering truths that were always true, that would be true even if no universe existed to instantiate them, even if no minds existed to comprehend them. The Pythagorean theorem doesn't depend on triangles existing. It's a relationship between abstract numbers true in all possible worlds. Maybe the Schrödinger equation is the same. Maybe quantum field theory describes a mathematical structure that exists necessarily, and the physical universe is just one particular realization of that structure. Max Tegmark, a cosmologist at MIT, took this idea to its logical extreme with his mathematical universe hypothesis. He argues that physical reality is mathematics. Not that it's described by mathematics, but that it is mathematics. That the universe doesn't just obey equations, it is an equation, or more precisely, a mathematical structure that exists in the space of all possible mathematical structures. In this view, asking why the laws of physics exist is like asking why the number 3 exists. It just does, in the same way all mathematical truths exist, eternally and necessarily, independent of any physical substrate. We happen to find ourselves in a universe that corresponds to a particular mathematical structure, one that allows for complexity and observers, but there's nothing special about our structure. It's one among infinitely many, all equally real in the Platonic sense. This is simultaneously comforting and horrifying. Comforting because it provides a foundation that doesn't itself need explaining. Mathematical truths are self-justifying. They're true by logical necessity. If the universe is mathematics, then asking where it came from is a category error, like asking what's north of the North Pole. It just is, and the question of origin doesn't apply. Horrifying because it means that every mathematically consistent structure exists, not as a possibility, but as an actuality. And somewhere in that infinite landscape of mathematical reality, There are universes far worse than anything you can imagine. Universes of pure suffering. Universes that last for a single Planck time and contain nothing but agony. Universes where the structure of logic itself is twisted in ways that would break your mind to contemplate. If all mathematical structures are real, then all possible hells are real too. And we're just lucky, or perhaps not lucky at all, to inhabit one of the more hospitable ones. But there's a problem with Platonism. It doesn't explain why this mathematical structure is instantiated physically. Why isn't mathematics just an abstract game, internally consistent, but disconnected from anything we'd call real? Why do we experience one particular mathematical structure, this universe, these laws, instead of floating in some formless space of pure mathematical abstraction? Tegmark argues that the question is backwards, that experience itself is part of the mathematical structure, that there's no gap between the abstract and the concrete. But this feels like wordplay. The fact that I'm conscious, that there's something it's like to be me, that I experience the passage of time and the sensation of existing, none of that seems reducible to an equation. And if it is, then what breathes fire into the equations and makes them real? The second camp rejects the idea that laws are eternal. Instead, it proposes that laws evolve, that they emerged alongside the universe, or perhaps because of it, shaped by a process analogous to natural selection. Lee Smolin, a theoretical physicist at the Perimeter Institute, developed this idea into a full cosmological theory called cosmological natural selection. His proposal? Universes reproduce through black holes. Every time a black hole forms, it spawns a new universe in a region of space-time disconnected from our own. A baby universe with slightly mutated physical constants. Most of these baby universes are duds. Their constants don't allow for complex structures, stars never form, no black holes are created, the lineage dies out. But some universes hit upon combinations of constants that favor star formation, which leads to more black holes, which leads to more baby universes, and over countless generations. The multiverse becomes dominated by universes fine-tuned for black hole production. Here's the clever part. The constants that favor black hole production also tend to favor life. You need long-lived stars, stable atoms, complex chemistry. The same conditions that allow black holes to form allow planets and organisms to emerge. So in Smolin's model, we don't need to invoke design or anthropic selection to explain fine-tuning. We're living in a universe descended from a long line of universes that happen to stumble upon constants conducive to complexity. The fine-tuning is a byproduct of cosmological evolution, not a cosmic accident or a divine hand on the dials. This is elegant, testable to some degree, and philosophically satisfying to those who dislike the arbitrariness of just-so constants. But it still doesn't fully solve the meta-problem. Where did the first universe come from? The one that started the whole chain. What determined the rules of reproduction? The mechanism by which baby universes inherit mutated constants? And what allows mutations in the first place? What's the deeper law that permits physical constants to vary across different universe generations? You've explained the diversity of laws, but not the meta-law that governs how laws can change. You've moved the mystery up one level, which is progress, but you haven't eliminated it. The third camp embraces the tautology. This is the anthropic principle in its strongest form, and it says, we observe these laws because we must. We can only exist in a universe where the laws permit our existence. Therefore, no matter how improbable our universe seems, no matter how finely tuned the constants appear, We should expect to find ourselves here because there's nowhere else we could be. This isn't an explanation. It's a selection effect. It's the observational equivalent of being surprised that you won the lottery when someone had to win, and the winner is by definition surprised. The anthropic principle comes in weak and strong flavors. The weak version is uncontroversial. Our observations are necessarily biased by the conditions required for observers to exist. Of course, we find ourselves on a planet at the right distance from a star, with liquid water and a protective atmosphere. If those conditions weren't met, we wouldn't be here to notice. The strong version is far more contentious. It says that the existence of observers isn't just a selection effect within one universe, but a selection effect across many universes. That there's a multiverse with countless variations in physical constants, and we necessarily inhabit one of the rare pockets where the constants allow for complexity and life. This explains fine-tuning without invoking design or evolutionary mechanisms. But it requires accepting the multiverse, which is a heavy metaphysical price. Is the anthropic principle an answer, or just giving up? It feels like the latter to many physicists. It says, don't be surprised that things are the way they are, because you couldn't observe them being any other way. Which is true, but unsatisfying. It's like asking why you were born in the 21st century and being told, because if you were born in the 11th century, you wouldn't be having this conversation. Technically correct, utterly unhelpful. The anthropic principle explains why we observe what we observe, but it doesn't explain why the framework exists in which anything can be observed at all. And this brings us face to face with the fine-tuning problem, which is either the strongest argument for something deeply strange going on, or the greatest statistical illusion in the history of science. Depending on who you ask, if the strong nuclear force were 2% weaker, carbon wouldn't exist. No carbon, no you. The strong force binds quarks into protons and neutrons into atomic nuclei. Too weak, and nuclei fall apart. You don't get anything heavier than hydrogen. No stars capable of fusion beyond the simplest reactions. No chemistry, no complexity. The universe becomes a thin soup of hydrogen atoms drifting in eternal darkness. 2%. That's the margin. If gravity were slightly stronger, stars would burn through their fuel in millions of years, instead of billions, too fast for life to evolve. If it were slightly weaker, stars wouldn't ignite at all. If the electromagnetic force were a bit different, atoms wouldn't form stable structures. If the cosmological constant, the energy density of empty space, were larger by a factor of 10, the universe would have expanded so fast that galaxies could never form. Matter would be diluted to irrelevance before gravity could pull anything together. There are 26 fundamental constants in the standard model of particle physics: the mass of the electron, the strength of the weak nuclear force, the charge of the quark. Each one seems arbitrary. There's no deeper principle we know of that predicts their values. They're just numbers we measure and plug into our equations. And yet, change any of them by a modest amount, and the universe becomes incapable of supporting life as we know it. Maybe some exotic form of life could exist with different constants, but the parameter space for any complexity at all is vanishingly small. Someone rigged the game, or you're a lottery ticket that won. 3 explanations vie for dominance. Design. An intelligence set the constants deliberately, fine-tuning the universe to allow for life. This is the God hypothesis, and it's fallen out of favor in physics not because it's been disproven, but because it's unfalsifiable and doesn't lead anywhere. You can't build a research program around God did it, accident, The constants are what they are by pure chance, and we happen to be in a universe that got lucky. This requires accepting that we're the beneficiaries of a coincidence so staggering it strains credulity, or selection bias. There are many universes with different constants, and we necessarily find ourselves in one of the rare ones that allows observers. This saves you from design and accident, but it requires accepting the multiverse, which many physicists view as too extravagant, an infinite proliferation of unobservable realities invoked to explain one. The anthropic principle says we're trapped in a tautology. We can't observe a universe that doesn't allow observers, so of course the universe we observe has the properties necessary for observation. This is logically airtight and emotionally hollow. It answers why these constants with "because you're asking," which feels like a cheat. But maybe it's not. Maybe the deepest truth about existence is that asking why you exist is like asking why language can talk about itself. The question contains its own answer, not because of some cosmic design, but because the structure of inquiry itself presupposes the conditions necessary for inquiry to occur. You can't ask questions from a state where questions are impossible, and therefore the fact that you're asking guarantees that you're in a state where asking is possible. The tautology isn't a bug. It's the fundamental feature of conscious experience. But if the multiverse exists, if there really are countless universes with different laws, different constants, different structures, then nothing becomes even stranger. Because then you need a mechanism generating universes, a process, a substrate, a framework that allows multiple cosmic realizations to emerge. The multiverse isn't free. It costs you a meta-universe, a higher-level structure that contains or produces the universes within it. And that meta-universe has its own rules, its own logic, its own unexplained existence. You've explained the diversity of universes at the cost of postulating a larger cosmos that needs explaining just as much as the original universe did. String theory offers one version of this. It predicts a vast landscape of possible universes, perhaps 10 to the 500th power different configurations, each corresponding to different ways the extra dimensions can curl up, each yielding different effective physical constants in the four-dimensional universe we experience. Eternal inflation offers another. Once inflation starts, it never fully stops everywhere at once. It continues in some regions, spawning new bubble universes, each potentially with different physics. Quantum mechanics offers a third through the many worlds interpretation. Every quantum measurement branches reality into multiple outcomes, and on cosmological scales, this could mean every possible universe exists in some branch. But all of these frameworks require rules. String theory requires the rules of string dynamics. Eternal inflation requires the rules of quantum field theory in curved space-time. Many worlds requires the unitary evolution of the wave function. You can't escape the problem. Every explanation invokes a deeper structure, and every deeper structure has its own unexplained architecture. Either you accept an infinite regress, rules explaining rules forever, with no bottom, or you accept a foundation that is itself unexplained, brute, given, just there for no reason. Or you accept that the question itself might be malformed, that asking where the laws came from is like asking what time it was before time existed. The grammar of the question presumes a framework that doesn't apply. Laws don't come from anywhere. They're not caused. They're not created. They're not selected. They're the boundary condition of explanation itself, the point at which all why questions terminate not because we've reached an answer, but because we've reached the limit of what why can mean. This isn't satisfying. It feels like giving up, but maybe it's not. Maybe it's recognizing that explanation has to stop somewhere, and wherever it stops will look arbitrary, will feel like it needs further justification. The laws of physics are either eternal, in which case they're more fundamental than the universe itself, more real than reality, or they emerged from something even deeper, in which case that deeper thing needs explaining. Neither option resolves the mystery. Both just relocate it. And yet, we're left with a universe that exists, laws that hold, constants that allow for complexity. You, reading this, thinking about it, conscious of the strangeness of your own existence. That's not nothing. That's not a mathematical abstraction or a Platonic form or a branching wave function. That's experience, direct and undeniable. And no amount of cosmology or quantum mechanics or philosophy has yet explained why there's something it's like to be you, why the universe doesn't just process information, but feels itself doing it. The laws before the laws remain hidden. Maybe they always will. Maybe they don't exist. Maybe existence itself is the foundation, raw and unexplained, and everything we call explanation is just us tracing patterns within existence, never stepping outside it to see where it came from. We've pushed the question as far as physics can take us. The next step requires changing the question entirely. Not, what caused the universe? Or, where did the laws come from? But something stranger, something that doesn't presume a beginning at all. What if the universe never started? What if the Big Bang wasn't the beginning, but the middle of an eternal process? Your birth certificate might be trillions of years wrong. We've been operating under an assumption so fundamental that questioning it feels almost absurd. The assumption is this: the universe had a beginning, a moment zero, a first instant, a boundary in time beyond which nothing existed. The Big Bang model tells us that 14 billion years ago, everything emerged from an infinitely dense point. And before that, well, before that is where the equations break down, where physics stops working, where we encounter a wall we've been calling the beginning. But what if that wall isn't a beginning? What if it's a transition, a doorway, a moment of transformation from one state to another? What if the universe didn't start at all? This isn't mysticism. It's a serious possibility emerging from several independent lines of theoretical physics, each approaching the problem from a different angle, each arriving at the same radical conclusion. Maybe the Big Bang was just an event in an ongoing process, one beat in an eternal cosmic rhythm. And the question of ultimate origin, why is there something rather than nothing, dissolves because there was never a moment when nothing was all there was. Imagine the universe is a phoenix. We're living in the feathers. The first alternative is the cyclic universe, and it's one of the oldest ideas in human thought. The ancient Hindus conceived of time as an endless series of cycles, each lasting billions of years, with creation and destruction following one another in eternal succession. The Stoics believed the cosmos would periodically be consumed by fire and reborn from the ashes. These were philosophical or religious intuitions, but modern physics has given them mathematical teeth. In cyclic models, the universe doesn't begin. It recurs. It expands, reaches some maximum state, contracts, and then rebounds into a new cycle of expansion. The Big Bang, in this view, is a big bounce, the transition point where a previous universe collapsed down to extreme density and then exploded outward to become our universe. And our universe will eventually do the same. collapsing into another bounce that births yet another cosmos. Roger Penrose, the Nobel laureate who helped prove that black holes must form singularities in Einstein's theory, proposed one version of this called conformal cyclic cosmology. His idea is elegant and strange. He argues that the far future of our universe, trillions upon trillions of years from now, when all the stars have died, all the black holes have evaporated through Hawking radiation, and the cosmos is nothing but a thin soup of photons, and other massless particles expanding into infinite dilution is mathematically equivalent to the Big Bang. The end and the beginning have the same geometric structure if you use the right mathematical transformation. So in Penrose's model, each cycle, or aeon, ends in a state that seamlessly becomes the Big Bang of the next aeon. There's no singular moment of creation. There's just an endless chain of universes, each emerging from the ashes of the previous one, like a cosmic Ouroboros eating its own tail forever. The appeal is obvious. You don't need to explain where the first universe came from because there is no first universe. The chain stretches infinitely into the past. Every answer to what came before is just another universe, another cycle, another bounce. The question of ultimate origin is sidestepped entirely. The universe exists because it has always existed, cycling through phases, never truly beginning, never truly ending. But even if the cyclic model is correct, it doesn't escape all problems. Thermodynamics throws up a red flag. The second law says that entropy, disorder, increases over time in a closed system. Each cycle should be messier than the last, more disordered, more chaotic. But we observe a universe that started in a remarkably low entropy state, highly ordered, with matter distributed smoothly and energy in forms that could be harnessed to do work. How does a cyclic universe reset its entropy? How does it go from maximum disorder at the end of one cycle to minimal disorder at the start of the next? Penrose has proposals involving the loss of information in black holes and the erasure of mass scales, but they're speculative, untested, and not universally accepted. The cyclic model trades one mystery, creation from nothing, for another. How does the universe rewind the clock on disorder? And there's a deeper issue. Even if universes cycle, what determines the rules that govern the cycling? What causes the bounce instead of a true singularity? What ensures that each cycle has the same physics, the same constants, the same potential for complexity? You still need a framework, a meta-law that governs the transitions between cycles. The cyclic model might eliminate the need for an absolute beginning, but it doesn't eliminate the need for laws that were never themselves created. If the universe is cyclic, then every moment, including this one, has happened infinite times before. Are you a rerun or an original? Is your life a pattern that's been traced and retraced across infinite aeons? A cosmic déjà vu that never remembers itself? The second alternative is eternal inflation, and it approaches the problem from a completely different direction. In the 1980s, Alan Guth and Andre Linde developed inflationary cosmology to solve certain puzzles about the early universe. Why it's so homogeneous, why it's so flat, why we don't see magnetic monopoles. Their answer: in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, doubling in size every tiny fraction of a second, inflating from something smaller than a proton to something larger than a grapefruit in far less time than it takes light to cross an atomic nucleus. This stretches out any initial irregularities, making the universe appear smooth and flat, and dilutes exotic particles like monopoles to undetectable levels. But here's the twist. Once inflation starts, it's almost impossible to stop everywhere at once. Quantum fluctuations in the field driving inflation mean that some regions stop inflating while others continue. The regions that continue keep expanding exponentially, and within them, more fluctuations occur, creating more regions that stop and more that continue. It's a fractal process, self-perpetuating, never-ending. Eternal inflation. Our Big Bang was just one bubble, one region where inflation stopped, and the energy driving it decayed into matter and radiation. But beyond our observable universe, inflation continues, spawning bubble after bubble after bubble, each potentially with different physical constants, different laws, a multiverse of staggering diversity. In eternal inflation, there's no beginning. Or rather, there might have been a moment when inflation started in some initial patch of space, but once started, it generates infinite future time and infinite space. The process has no natural endpoint. Our universe, by which I mean our observable patch, the region causally connected to us, is 14 billion years old. But the multiverse, the eternally inflating background, could be infinitely old, or it could have begun a finite time ago and will continue forever. Either way, asking what came before our Big Bang is answered with eternal inflation was happening, and a quantum fluctuation caused inflation to end in our patch, triggering what we call the Big Bang. In eternal inflation, an infinite number of yous exist. In fact, every possible version of you is reading this right now, somewhere. Because if there are infinite bubble universes and each one undergoes infinite spatial inflation, then every possible arrangement of matter will eventually be realized. There will be bubbles that are nearly identical to ours, where history played out almost the same way, but you sneezed at a different moment. There will be bubbles radically different, where the constants of nature vary and life takes forms we can't imagine. There will be bubbles where you don't exist at all, and bubbles where everyone is you. Infinity is big enough to contain everything that can possibly happen, and eternal inflation guarantees that everything happens somewhere. But even if eternal inflation is correct, it still requires a mechanism to start inflating. Where did the inflaton field come from? The hypothetical field that drives the exponential expansion? Where did the energy come from? Why does the field have the particular potential energy curve that makes inflation eternal rather than finite? You can invoke quantum fluctuations, but quantum fluctuations need a quantum vacuum, and a quantum vacuum needs laws, and we're back to the same problem. Eternal inflation might eliminate the need for our Big Bang to be an absolute beginning, but it doesn't eliminate the need for something to exist prior to or alongside inflation. The multiverse generator still needs explaining. The third alternative comes from loop quantum gravity, an attempt to merge quantum mechanics with general relativity by treating space-time itself as quantized, made of discrete loops rather than being a smooth continuum. In this framework, the singularity at the Big Bang isn't really a singularity. It's the minimum possible scale, the Planck scale, where space-time is granular like pixels on a screen. You can't compress things further because there's no further to go. And when you run the equations of loop quantum gravity backward in time through the Big Bang, something remarkable happens. Instead of hitting an infinite density singularity, the universe bounces. The equations show that our expanding universe could have emerged from a previous universe that was contracting. At the moment of maximum compression, quantum effects dominate, preventing true collapse, and the energy rebounds outward. The Big Bang becomes a big bounce, a transition from contraction to expansion. This is profoundly different from the cyclic models we discussed earlier. It's not saying the universe goes through infinite cycles of expansion and contraction. It's saying that our particular universe might have bounced once from a previous state, and that previous state might have its own history stretching back. Or maybe it bounced multiple times. Or maybe the bounce is a generic feature, and every universe that reaches extreme compression bounces into a new expansion phase. The details are still being worked out, and the model depends on exotic physics, quantum gravity, that we haven't confirmed experimentally. But if it's correct, then the Big Bang wasn't a beginning. It was a turning point, the moment when the universe stopped shrinking and started growing. No more special than the moment when a ball thrown upward stops rising and starts falling. But even if the bounce is real, it doesn't solve the ultimate mystery. What was the state before the previous contraction? Was there a bounce before that? Does the chain extend infinitely into the past, or was there a first bounce? And if so, what triggered it? And what determines the physics of the bounce itself? Loop quantum gravity provides the mechanism, quantum effects preventing the singularity. But it still needs laws, structure, a framework in which loops and bounces are possible. You've avoided the singularity, which is an achievement, but you haven't avoided the deeper question of why there's a framework at all. What all three of these models have in common is a rejection of the idea that the Big Bang was an absolute beginning. They say the universe, or the multiverse, or the eternal process that generates universes has no starting point. And maybe that's the right answer. Maybe beginning is a human bias. We're creatures embedded in time, experiencing it as a flow from past to future. We have births and deaths. Stories have opening chapters. Buildings have foundations. We crave starting points because that's how our minds organize information. But the universe isn't a story. It's not required to have a narrative structure that satisfies our need for origins. What if the universe is like a circle, where asking, "Where does it start?" is the wrong question? There is no start. There's just the circle, eternal and self-contained, with no privileged point that deserves to be called the beginning. This is philosophically liberating and terrifying in equal measure. Liberating because it dissolves the paradox of creation. If there was never a first moment, then you don't need to explain what caused the first moment. The causal chain is infinite, or loops back on itself, and the question of ultimate origin simply doesn't apply. Terrifying because it means existence has no foundation, no grounding point, no bedrock on which everything rests. It's processes all the way down, or cycles all the way around, with nothing at the center, nothing holding it up, nothing justifying why this process rather than some other, or no process at all. So if the universe didn't start, if our Big Bang was just a bounce, or a bubble, or a phase transition in an eternal cycle, are we asking the wrong question entirely? Maybe the question shouldn't be, why is there something rather than nothing? But, why is there time rather than timelessness? Or, why does change happen rather than eternal stasis? Or, why is existence structured rather than formless? These questions don't presume a beginning. They presume a framework, a structure, a set of possibilities, and maybe that's the real mystery. Not that the universe began, but that it continues. Not that something emerged from nothing, but that the patterns we call something are stable enough to persist, complex enough to generate observers, structured enough to be comprehensible. We've traveled through cyclic universes, eternal inflation, quantum bounces. We've seen how physics might eliminate the need for an absolute beginning, how the Big Bang might be a middle chapter in an infinite book. But none of these models escapes the deeper puzzle. They all require rules, frameworks, structures that themselves have no origin. Either those structures are eternal, in which case they're the ultimate brute fact, or they emerged from something even deeper, in which case the question just repeats. There's no escape, no final answer that doesn't rest on something unexplained. Unless the question itself is the problem. Unless asking why presumes a kind of answer that doesn't exist. Unless explanation reaches a natural limit, and we're staring at it, demanding it be something other than what it is. The universe exists, time flows, things change, patterns emerge, consciousness arises. These are facts, observable, undeniable. And maybe facts don't need justification. Maybe they just are. And the human compulsion to ask why is a tool that works beautifully within the universe, but breaks when applied to the universe itself. We're about to step beyond physics into philosophy, where the question, why is there something rather than nothing, might be unanswerable by design. If nothingness is more natural than something, then existence is the universe's biggest mistake. But who's judging? We've pushed physics to its limits. We've explored quantum fluctuations, cyclic universes, eternal inflation, mathematical structures existing in Platonic realms. We've seen how the Big Bang might not be a beginning, how nothing might be inherently unstable, how the laws of physics might be eternal or emergent or selected through cosmic evolution. And yet, beneath all of it, unresolved and perhaps unresolvable, sits a question that refuses to go away. A question so simple a child could ask it, so profound that 3 centuries of philosophy haven't answered it. Why is there something rather than nothing? Gottfried Wilhelm Leibniz posed this question in the 17th century, and it echoed through the halls of philosophy like a bell that won't stop ringing. Not, what caused the universe, or how did the Big Bang happen? But the more fundamental challenge, why does anything exist at all? Why is there a stage, actors, a play? Why not just absence? Pure, total, absolute non-existence? No universes, no multiverses, no quantum fields, no mathematical structures, no God, no Platonic realm, nothing. Why is reality populated rather than empty? And don't say, because of quantum mechanics, or because of the laws of physics, because those are part of something. The question is asking why there's a something category rather than the alternative, which is that there might have been no category at all. Trying to explain existence is like asking a fish to describe water. We're inside the thing we're trying to understand. Every thought we have, every concept we grasp, every tool we use to analyze reality is itself part of reality. We can't step outside existence to examine it from a neutral vantage point. We can't compare reality to non-reality because there's no place to stand where both are accessible for inspection. We're trapped inside the phenomenon we're trying to explain, using tools made from the phenomenon, following rules embedded in the phenomenon. It's the ultimate epistemological prison. Leibniz believed in the principle of sufficient reason. This principle says that everything must have an explanation. Every fact, every state of affairs, every true proposition has a reason for being the way it is, rather than some other way. Nothing is arbitrary. Nothing is brute. For Leibniz, this principle was self-evident, a bedrock of rational thought. If something exists, there must be a reason it exists. And that reason must itself have a reason, and so on, until you reach a necessary being, something that exists by its own nature, that couldn't fail to exist, whose essence is existence itself. For Leibniz, this was God. The chain of explanation terminates in a being that is self-explanatory, that contains within itself the reason for its own existence. This is elegant, logically consistent, and utterly question-begging, because now you have to explain why a necessary being exists rather than no necessary being. You've moved the mystery, not solved it. Saying God exists necessarily just shifts the question to, why is necessary existence a thing that's instantiated? You can say God's nature is such that non-existence is impossible, but that's just asserting what needs to be proven. It's saying, this particular thing exists because it's the kind of thing that must exist, which is circular. And even if you accept it, you haven't explained why the framework exists in which necessity and impossibility are meaningful categories. The alternative position rejects the principle of sufficient reason. It says that not everything needs an explanation. Some facts are brute. The universe exists, and that's just how it is. There's no deeper reason, no hidden cause, no ultimate justification. Existence is the foundational fact from which all explanations proceed. But it doesn't itself have an explanation because explanation has to stop somewhere. And this is where it stops. Deal with it. This position is philosophically unsatisfying, but logically unassailable. If you demand an explanation for everything, you get an infinite regress. If you stop the regress by invoking a necessary being or a self-explanatory principle, you're smuggling in an exception to your own rule. So maybe the clean answer is to admit from the start that explanation reaches a limit, that some facts are primitive, foundational, given. The universe exists. That's the brute fact. Everything else we call explanation is just tracing patterns within that fact, never stepping outside it to see why the fact obtains. But which is more intellectually honest? To say, there's a reason and it's this, while admitting you can't justify the reason itself? Or to say, there's no reason, it just is, and accept that the human craving for explanation will never be fully satisfied? Both positions leave you in the same place, staring at something unexplained, something that either explains itself, which sounds like magic, or needs no explanation, which sounds like giving up. Derek Parfit, the British philosopher who spent decades wrestling with these questions, laid out a spectrum of possibilities. At one end, nothing exists. This is logically possible. There's no contradiction in the concept of absolute non-existence. It's just not the world we find ourselves in. At the other end, everything that can exist does exist. This is Tegmark's Level 4 multiverse, where every mathematically consistent structure is realized. Every possible universe is actual. In between, some things exist but not others. And we need to explain why this particular subset, rather than a different one. Parfit asked, which of these states of affairs is most likely, most natural, requires the least explanation? You might think nothing exists is the simplest, the default, the state that needs the least justification. After all, nothingness requires no mechanisms, no laws, no structure. It's the absence of all complexity. But Parfit argued that's not obviously true. Because nothing exists is a very specific state of affairs. It's not just the absence of universes, it's the absence of everything. The absence of laws, of potentiality, of possibility. That's a constraint. It's saying, Out of all the things that could be, precisely 0 of them are instantiated. Why that constraint rather than no constraint? Why perfect emptiness rather than infinite fullness? On the other hand, everything exists also seems simple in a way. It's unconstrained. No selection, no filter, no mechanism deciding what gets to be real and what doesn't. Every possibility is realized because there's nothing preventing it. This is maximally symmetric, maximally egalitarian. But it requires a framework in which everything possible is a coherent category, and that framework is itself something. It requires modal space, the space of possibilities, to be real in some sense. And that's not nothing. So maybe the middle ground is the strangest of all. We observe that some things exist: atoms, galaxies, consciousness, this conversation, but not everything. Philosophers call this modal selectivity. Reality chooses or is chosen from the space of possibilities. And that choice, that filter, that mechanism of selection needs explaining more urgently than either extreme. Why these laws and not others? Why this universe and not a different one? Why the particular configuration we call reality rather than the infinite other configurations that seem just as possible? There are 10 to the 500th power possible universes in string theory. If you picked one at random, it would be sterile. No stars, no planets, no complexity. The constants would be wrong. Chemistry wouldn't work. Structures wouldn't form. We hit the jackpot. Or we're the only players. And this brings us to the most unsettling question of all. Is nothingness even coherent? Can we truly conceive of absolute non-existence, or does the act of thinking about it create something? When you imagine nothingness, what are you imagining? A black void? That's something. Space with a color. Empty set? That's a mathematical object, still something. The absence of all things? But absence is a concept, a placeholder, a way of organizing thought. It exists, at least in your mind. And if nothingness can't even be coherently conceived, then maybe it's not a real possibility. Maybe nothing is a grammatical construct that doesn't correspond to anything metaphysically possible. Maybe the question why, something rather than nothing, is like asking, why are there circles rather than square circles? It presumes an alternative that isn't actually an alternative. Some philosophers have argued exactly this. They say that absolute nothingness would violate certain logical or metaphysical principles, that existence is in some sense necessary, that the idea of there might have been nothing is incoherent once you examine it closely. But this feels like wordplay. The fact that we have trouble imagining nothingness doesn't mean it's impossible. It might just mean our cognitive tools are poorly suited to the task. After all, we have trouble imagining four-dimensional space, but that doesn't mean space-time isn't real. Robert Nozick, the philosopher who explored these questions in his book Philosophical Explanations, asked the question starkly, why is there anything at all? No one has answered him satisfactorily in 50 years. Maybe no one ever will. Because every answer either invokes something that itself needs explaining, or it declares by fiat that this particular thing needs no explanation. Neither move feels like progress. It's just choosing where to place the mystery. At the beginning, in a necessary being, or, at the end, in a brute fact. And here's where the existential weight crashes down. If the universe's existence is unexplained, if it's either a brute fact or rests on a necessary being that's itself inexplicable, then what does that do to meaning? If there's no ultimate reason for anything, If the foundation of reality is arbitrary or self-justifying but not justified, does meaning collapse? Does purpose evaporate? Do our lives, our choices, our struggles become cosmically insignificant? Or does it free us? Does the absence of cosmic justification mean we're free to create our own meaning, unbounded by some grand design or divine plan? If the universe doesn't exist for a reason, then it doesn't impose a reason on us. We're not here to fulfill some preordained purpose. We're here because existence happened to unfold in a way that produced us. And what we do with that existence is up to us. The lack of ultimate grounding becomes liberation rather than nihilism. This is the existentialist move. Camus, Sartre, Nietzsche in his own way. They embrace the absurdity. The universe has no inherent meaning, and that's okay. Meaning is something we construct, something we choose, something we enact through our decisions and commitments. The fact that existence is groundless doesn't make it worthless. It makes it open, plastic, responsive to will. You're not reading a script written by the cosmos. You're improvising your part in an ongoing performance that has no author, no director, no final act. But you have to feel the void first. You have to stare into the abyss of unexplained existence and feel its coldness, its indifference, its refusal to justify itself. You have to acknowledge that the universe doesn't care why it's here, doesn't know why it's here, doesn't need to know. And then, from that acknowledgement, you either despair or you choose. You either let the meaninglessness crush you, or you accept it and build meaning anyway. Not because it's cosmically sanctioned, but because it's what conscious beings do. We create, we connect, we love, we struggle. We make things matter, even though they don't have to matter. The philosophical abyss is that there is no bottom, no final answer, no ultimate explanation, no resting place where the questions stop and satisfaction arrives. Every explanation opens onto a deeper mystery. Every answer prompts a further question. The chain of why extends infinitely, or loops back on itself, or terminates in something unexplained. And none of those options provides the closure we crave. We're beings who need reasons existing in a reality that might not have one. And maybe that's the point. Maybe the discomfort we feel when confronting this question, the vertigo, the existential unease, the sense that something is deeply wrong or deeply right, but we can't articulate which. Maybe that discomfort is the appropriate response. Maybe existence is genuinely strange, genuinely paradoxical, genuinely beyond our categories. And recognizing that isn't failure. It's the beginning of wisdom. Philosophers have been asking, why is there something rather than nothing, for centuries? Scientists have pushed the question to the edge of testability with quantum cosmology and multiverse theories. And we're no closer to an answer than Leibniz was, not because we're not smart enough, but because the question might be unanswerable in principle. Not because it's too hard, but because it's asking for a kind of explanation that can't exist. An explanation of explanation itself, a reason for reasons, a foundation that stands on nothing. Maybe the answer isn't in equations or philosophy. Maybe it's in acceptance of the mystery. Not giving up, but recognizing that some questions mark the boundary of what questions can ask. That existence is the context in which all answers occur, and you can't step outside the context to explain why there's a context. That the universe exists, we exist, and the fact that we can ask why is itself a kind of answer, not to the question we asked, but to a different question. Not why something rather than nothing, but what are we, that we can wonder about this? We're the part of the universe that became conscious enough to question its own existence. That's not a solution to the mystery. That's a deepening of it. And maybe that's all we get. The mystery, the wonder, the awareness that we're staring at something vast and inexplicable, and it's staring back through our eyes. Every answer we've explored makes existence either miraculous or meaningless. Somehow, both feel true. We've journeyed from the quantum foam to platonic realms, from cyclic universes to eternal inflation, from mathematical necessity to philosophical surrender. We've watched the Big Bang dissolve from a moment of creation into a transition, a bounce, a bubble in an infinite froth. We've seen how nothing might be unstable, how the universe could tunnel into existence from a state so minimal it barely deserves a name, how the laws of physics might be eternal structures that never needed creating, or emergent patterns that crystallized from deeper chaos. We've explored the possibility that existence is a brute fact requiring no justification, and the alternative possibility that everything that can exist must exist. And we necessarily find ourselves in one of the pockets where observers are possible, and we're no closer to an answer. Not really. Oh, we've gained knowledge. We understand the mechanisms that might allow universes to emerge without external causes. We've pushed the boundary of ignorance back to the Planck epoch, to the moment when quantum gravity effects dominate and our equations surrender. We've mapped the terrain of possibility with mathematics and observation, confirmation and falsification. But the question that launched this exploration, why is there something rather than nothing, remains exactly as mysterious as when we started. Perhaps more so, because now we understand how many ways there are to not answer it. Science has given us the how matter behaves at extreme densities, how space can expand, how quantum uncertainty permits fluctuations, how energy might sum to zero, how universes might cycle or branch or inflate eternally. But science cannot, even in principle, tell us why. Why these laws and not others? Why a framework that permits universes rather than no framework? Why existence is the case rather than absolute absence? The tools of science are designed to explain phenomena within reality, not reality itself. Asking science to explain why there's a universe is like asking a microscope to examine itself. It's the wrong tool for the job, and the job might not be doable. Imagine the universe as a question mark, where the dot at the bottom, insignificant in scale, but necessary for the symbol to mean anything. So where does that leave us? We've been presented with a spectrum of possibilities, each pulling us in a different emotional and philosophical direction. If the universe is a quantum fluctuation, a random blip in the void that happened to inflate and persist, does that cheapen everything? Does it mean your life, your loves, your struggles are cosmically accidental? A side effect of probability playing out over infinite time? Or does it liberate you? Does it mean you're not here to serve some preordained purpose? Not fulfilling a role in a cosmic drama scripted before you were born? You're a genuine surprise, an emergence that didn't have to happen. And everything you do with your existence is authentically yours. The universe didn't create you for a reason. That means you get to decide what the reason is. If the laws of physics are eternal, Platonic structures existing necessarily in some abstract realm, then existence has a kind of inevitability. The universe couldn't have failed to exist because the mathematical structures that describe it are logically necessary. You're not an accident. You're a consequence, a theorem proven by reality itself. But does that give you dignity or strip it away? Are you a character in someone else's equation? A pattern that had to emerge once the axioms were set? Or are you proof that consciousness, meaning, and choice are woven into the deepest structure of reality, that the universe is fundamentally hospitable to creatures who can understand it? If we live in a multiverse, selected by anthropic necessity from an infinite variety of possible universes, then our existence is explained by observer selection bias. We're here because we can only be in a universe that allows us to be here. Other configurations exist, sterile, lifeless, hostile, but no one's there to ask why. Does this make you lucky? Or does it make you trapped in a tautology? Your existence explained by the fact that you exist, circular and unsatisfying. The multiverse explains fine-tuning without invoking design, but it does so by multiplying mysteries. Now you have to explain why there's a mechanism generating universes, why the multiverse has the particular structure it does, why observer selection is a principle that applies. If the universe is cyclic, eternal, never beginning and never ending, then your life is one moment in an infinite sequence. Perhaps this exact moment has occurred before, countless times, and will occur again, countless times more. Does that make your choices meaningless, mere echoes in an endless repetition? Or does it grant you a kind of immortality, a guarantee that this pattern you call yourself will be traced again, re-experienced, relived? The Stoics found comfort in eternal recurrence. Nietzsche found it simultaneously horrifying and liberating. The same fact, different emotional responses, neither more correct than the other. If existence is a brute fact, unexplained and unexplainable, the foundation on which all explanations rest, but which itself has no foundation, then you're adrift in a cosmos that doesn't justify itself. There's no cosmic parent to ask why and receive an answer. The universe just is, and so are you. And meaning is whatever you construct from the raw material of experience. This is either the death of hope or its birth, depending on whether you need external validation for your life to matter. Every path leads to discomfort. Every answer feels incomplete. The universe either rests on something unexplained, making explanation circular, or it rests on nothing, making existence absurd. Neither option satisfies the human need for grounding, for reasons that go all the way down, for a foundation that doesn't require its own foundation. But here's the thing. Here's what we've been circling around for 20,000 words without quite saying directly. The discomfort isn't a bug. It's a feature. The fact that no answer satisfies us completely isn't a failure of our theories or our philosophy. It's a signal, a sign that we're pushing against the limits of what questions can ask, what answers can provide, what understanding can mean. We are matter that learned to think. Atoms forged in the cores of dying stars, scattered across space, collected by gravity into a planet, organized by chemistry into cells, shaped by evolution into brains that can contemplate their own origin. The universe has been here for nearly 14 billion years, and for most of that time, no part of it wondered why. Galaxies formed, stars burned, planets coalesced, entirely unconscious, entirely unreflective. And then, in at least one corner of one galaxy, complexity crossed a threshold. Neurons connected in patterns dense enough that sensation became experience. Experience became memory. Memory became self-awareness. Self-awareness became the capacity to ask, why am I here? You're made of atoms from exploding stars, thinking about how those stars got here. If that's not sacred, what is? The question, why is there something rather than nothing, might be unanswerable. But the fact that we can ask it, that the universe produced entities capable of wondering about their own existence, is itself a kind of answer. Not to the question we asked, but to a question we didn't know we were asking. The universe isn't just a collection of particles obeying equations. It's a process that generates meaning, purpose, curiosity, wonder. These aren't external properties we project onto a meaningless void. They're things the universe does, capacities it has, modes of its being, the odds of you existing. 1 in 10 to the 2,685,000th power. That's not a metaphor. That's a calculation, accounting for the specific arrangement of genes, the specific meeting of ancestors, the specific chain of events stretching back through evolutionary history to the first replicating molecules. Change any link in that chain, and you wouldn't be here. Someone else might be, or no one at all. The odds of the universe existing, unknown. We don't have a sample size. We don't know if universes are common or rare, or if the concept of probability even applies. Both happened anyway. Against whatever odds, through whatever mechanism or lack thereof, existence occurred. And within that existence you occurred. And you're wondering about it. That's not nothing. That's everything. We may never know why the universe exists. The question might dissolve under sufficient scrutiny, revealed as a grammatical artifact rather than a genuine mystery. Or it might be the deepest question there is, forever unanswerable because it asks about the preconditions for answers themselves. Either way, we're left with the reality of our situation. We exist, we're conscious, we care about things, we form connections, pursue goals, experience joy and suffering, create and destroy, love and grieve. And none of that requires cosmic justification to be real, to matter, to be worth doing. The universe might not have a reason. It might be a brute fact, a quantum accident, a mathematical necessity, or something stranger still that we haven't conceived. But here's what we know with absolute certainty. You can have reasons. You can choose what matters to you. You can decide what to do with the improbable gift of consciousness, this brief window of awareness in a cosmos that spent eons unconscious, and will spend eons more that way after you're gone. This isn't nihilism. It's the opposite. It's recognizing that meaning doesn't require external grounding. That purpose doesn't need to be handed down from on high. That your life can be significant even if, especially if, the universe doesn't impose a significance on it. You're free, terrifyingly, gloriously free. Free to make mistakes, to choose wrong, to waste time, to fail. And free to create beauty, to reduce suffering, to connect with others, to understand something new, to leave the world different than you found it. The mystery remains. The question sits unanswered, perhaps unanswerable. We've explored the horizons of physics and brushed against the boundaries of philosophy, and we've found no final resting place, no answer that resolves all tension and lets us stop asking. But we've found something else. We've found that we're the universe examining itself, questioning itself, wondering about itself. We're not observers from the outside looking in. We're the inside looking at itself, and the looking is part of what the universe is. So carry the question lightly. Let it sit with you, not as a weight, but as a companion. Let it remind you that existence is strange, that being here is improbable, that consciousness is a gift with no return address. Let it make ordinary moments extraordinary, because behind every ordinary moment is the most profound mystery there is, that anything exists at all. We are stardust contemplating stars. We are the universe's way of knowing itself. We are the question and the questioner, the mystery and the witness to the mystery. And whether that's an accident, a necessity, or something beyond our categories entirely. We're here now, aware, alive, asking why, and in the asking, creating the only answer we'll ever have. The universe might not have a reason, but you can.